In this video, let's go ahead and explore the concept of conservation of momentum. Hi, this is Dr. Vani and welcome to E3 STEM Academy. As we all know, momentum is the product of mass and velocity, and it is a vector quantity and has a direction associated with it. Now, before we explore the concept of conservation of momentum, let's step back and talk a little bit about collisions. A collision is simply an interaction between two or more objects. Collisions are of three kinds: elastic collisions, inelastic collisions, and perfectly inelastic collisions. It does not matter what type of collision it is. It is important for you to understand that momentum is always conserved in all types of collisions. Elastic collision is one in which there is conservation of both energy and momentum. Most of the collisions that we see are not elastic in nature. Because there is friction, there is always going to be some amount of energy that is going to get converted to heat, light, or sound. But often, when the friction is negligible, we can assume that it is an elastic collision. For example, billiards. When we play billiards, we can assume that the collisions as elastic collisions. Or when we are on a skateboard, and if the friction is negligible, then we can assume those collisions to be elastic in nature. So when we are ignoring friction, we can assume the collisions to be elastic in nature. But realistically, there is no collision that is perfectly elastic in nature. Now, what is an inelastic collision? In an inelastic collision and perfectly inelastic collision, only momentum is conserved. Now, then what is the difference between inelastic and perfectly inelastic? In a perfectly inelastic collision, objects move with the same final velocity after collision. So, for example, let's assume there is an object of mass m and another object b of mass capital M. And let's say m is moving with a velocity v and object b is actually at rest. Now, after collision, the object A and object B combine together and move with a velocity Vf. Such kind of collisions are called perfectly inelastic collisions. In a perfectly inelastic collision, objects combine together and move as one entity with the same final velocity. It is important for you to notice that in both inelastic and perfectly inelastic collisions, only momentum is conserved and not kinetic energy. Now let's go ahead and understand what is the meaning of conservation of momentum. Let's say we have two masses, m1 and m2. m1 is moving with a velocity of v01. m2 is moving towards m1 with a velocity of v02. Now these two objects, m1 and m2, collide, and after collision, m1 moves off or bounces off with a velocity of vf1, and m2 bounces off with a velocity vf2. Conservation of momentum basically states that the sum of the initial momentums of the two objects. So when I'm talking about sum here, I'm not talking about the individual initial momentums. I'm talking about the sum of the initial momentums of both the objects together, which is going to be m1 v01 plus m2 v02. So this is the sum of the initial momentums of the two objects is always going to be equal to the sum of the final momentums of the two objects. So that means it's going to be equal to m1 vf1 plus m2 vf2. Now, it is very important for you to understand that momentum is a vector quantity, and the direction of the momentum is going to be the direction of the velocity. So understand that you have to pay attention to the direction of the velocities. If the object is moving to the right, then we know that that velocity is positive, and if the object is moving to the left, we take it as negative. So direction is extremely important, and you have to take that into consideration. Again, we are not talking about the conservation of momentum of the individual objects that are taking place in a collision. We are talking about the sum of all the initial momentums and the sum of all the final momentums. I hope the concept is clear. Now let's go ahead and apply this concept to a free response question.
Okay, let's go ahead and take a look at this problem. It says several students are riding in bumper cars at an amusement park. The combined mass of car A and its occupants is 250 kilograms. The combined mass of car B and its occupants is 200 kilograms. Car A is 15 meters away from car B and moving to the right at 2 meters per second. Now, again, keep in mind that when you're dealing with momentum, momentum is a vector quantity, right? So you have to pay attention to the directions, and it says it's moving to the right, and therefore this is going to be, in other words, they're telling you that this 2 meters per second is positive. When the driver decides to bump into car B, which is at rest, so the initial velocity of car B is 0. That's also given to us. Part A. Car A accelerates at 1.5 meters per second square to speed of 5 meters per second and then continues at constant velocity until it strikes car B. Calculate the total time for car A to travel the distance of 15 meters. So they're asking us to calculate T total. Now, first thing you need to understand is this car is starting off with a velocity of 2 meters per second. It is accelerating to the right at a rate of 1.5 meters per second square to a speed of 5 meters per second. I do not know how far it is traveling before it is reaching a speed of 5 meters per second. I do know that it is accelerating at 1.5 meters per second square. And then continues with the same velocity for the rest of the distance before it bumps into that car B. So let's assume that car A traveled a distance x before its velocity changed to 5 meters per second. So initial for that part, right, for the part of x displacement or for that distance traveled, the initial velocity is going to be 2 meters per second and the final velocity is going to be 5 meters per second. once it reaches that 5 meters per second speed, then the remaining distance, which is 15 minus x meters, right? For the remaining distance of 15 minus x meters, it is moving with the same speed of 5 meters per second. I hope the problem is clear, right? Now they're asking you what would be the total time taken for that entire 15-meter distance. So if I call for this x distance, if I call the time as t1, and for the second part, if I call it as t2, I'm looking for t1 plus t2, which is my t total. Now the question is, how are we going to find that t1 and t2? So if I can find T1 and T2, then we're just going to add them together to get that total time. So how are we going to find T1 and T2? So I know for this distance of x, the car is accelerating at a rate of 1.5 meters per second squared. So I know acceleration, which is 1.5 meters per second squared. I also know that it is reaching a velocity of 5 meters per second. So I do know that the final velocity for this x distance is 5 meters per second. And of course, they gave us V0, and that V0 is equal to 2 meters per second, right? They gave it to us. So I can find time using the definition of acceleration. Acceleration is Vf minus V0, which is the change in velocity over time, right? So the time would be equal to change in velocity over acceleration. So if I go ahead and find, so this is my T1, right? So if I find my T1, which is change in velocity, so that's going to be 5 minus 2 divided by 1.5 meters per second squared, which is my acceleration, then T1 is going to be 3 divided by 1.5, and that's equal to 2 seconds. Right? Now I can go ahead and find T2. How are we going to find T2? If I can figure out x, then I can figure out 15 minus x. And if I can figure that out, I know that for that distance of 15 minus x, the car is traveling with constant speed of 5 meters per second. And so I know V is equal to delta x over t. And the delta x here is 15 minus x over t2. The problem is I do not know x. If I can figure out x, then solving for t2 is going to be pretty easy. So first we need to solve for x. Let's see how to solve for x. So again, I'm going to use the same information that I have here. I know acceleration, I know Vf, I know V0. I want to find x. I'm going to go ahead and use delta x is equal to V0 times t plus 1/2 at squared. I'm going to use that kinematic equation, and I'm going to solve for delta x. Let's go ahead and solve it. So delta x is going to be equal to V0 is 2 times time is 2 plus 1/2, a is 1.5, and t square is going to be 4 because 2 square is 4. So now I can figure out delta x. This is going to be 2 times 2, that is 4, plus 1/2 of 1.5 times 4 is going to be 3. And so that distance is going to be 7 meters. So in that time of 2 seconds, right? In that time of 2 seconds, the car actually traveled a distance of 7 meters. So this right here is 7 meters. So if this distance is 7, I know how much would be this distance, 15 minus 7, and that is going to be 8 meters. Right? Now that I know the distance and I know the speed, I can figure out T2. I can figure out T2 very easily. So T2 is simply going to be equal to 15 minus x, which is going to be 8 divided by the velocity, which is 5, right? 5 meters per second is the velocity for that distance of 15 minus x. So now you're going to divide these. So 8 divided by 5, and that's equal to 1.6 seconds is your T2. So I have T1 and T2. Now you add those together. So it's going to be 2 plus 1.6 seconds, which would be equal to 3.6 seconds. This is the total time it would take for the car to travel a distance of 15 meters. Now part B. After the collision, car B moves to the right at a speed of 4.8 meters per second. Calculate the speed of car A after the collision. Very good. So we're going to use law of conservation of momentum because it doesn't matter what type of collision it is. Law of conservation of momentum is going to hold good, right? So what does law of conservation of momentum say? It's mass of car A times the initial velocity of car A plus mass of car B times the initial velocity of car B is equal to mass of car A times the final velocity of car A plus mass of car B times the final velocity of car B. We have all the information. All that we are missing is the final velocity of car A. So we're going to go ahead and solve. So MA, mass of car A, is 250 kilograms, right? So 250 kilograms times the initial velocity of car A. This is where you got to be careful because students end up using 2 meters per second, right? But keep in mind that it is not moving with a velocity of 2 meters per second when it goes and bumps into that car B. So the velocity with which it actually bumps into car B is 5 meters per second. So that is the part you've got to be careful with. If you've used 2, then you're going to get it wrong. So that is going to be 5 plus mass of car B is 200 times the initial velocity of car B is anyways 0 because it is at rest, is equal to 250 times, I do not know what the final velocity of car A is, plus 200 times it moved with a velocity of 4.8 meters per second to the right after collision. So because it is to the right, I know that that is positive. So times 4.8 meters per second. So this is anyways gone. That's going to be 0. So 250 times 5. How much is that value? $1,250.
Yeah.
Is equal to 250 V final of car A plus 200 times 4.8 is 960. I'm going to subtract 960 on both sides. So that goes away. And 1250 minus 960 is 290 is equal to 250 VFA. So if I want the final velocity of car A, that is simply going to be 290 divided by 250. And that's equal to 1.16 meters per second. Now watch, VFA is positive. It is positive 1.16 meters per second. And because it is positive, I know that this cart is actually moving to the right. See, in part 2 of B, they're asking you, indicate the direction of the motion of car A after the collision. So I know for a fact that because my velocity of car A is positive when I solve for it, I know that it is moving to the right. Is this an elastic collision? Is this an elastic collision? Yes or no? Justify your answer. Again, they're asking for justification. How do we justify whether a collision is elastic or not? Conservation of kinetic energy, right? If I can show that the total kinetic energy before collision and the total kinetic energy after collision is the same, then I know that that is an elastic collision. So you can go ahead and figure out K initial and K final. So if I'm looking at K initial, I'm looking at the kinetic energy of the two cars together before collision, right? I know that cart B is anyways at rest. So when it is at rest, it's not going to have any kinetic energy. So I'm going to calculate the kinetic energy of the 250 kilogram cart. So that is going to be 1/2 mv squared, and the velocity is 5. So 5 squared, that's 25 times 250 divided by 2. 3,125 joules. This is the initial kinetic energy of both the cars together before collision, right? Now I'm going to find the kinetic energy after collision. So that is going to be the sum of the two kinetic energies. I mean, like for both the cars, right? So 1/2 250 times the final velocity of cart B, I mean cart A is 1.16 meters per second. So 1.16 square of that plus 1/2 times 200 times the velocity of the 200 kilogram car after collision is 4.8. So 4.8 square of that. 2,472 joules is the total final kinetic energies of the cars, right? So if you notice, K0 is 3,125 joules and K final is 2,472 joules. And because K0 is not equal to Kf, I know that this is not an elastic collision. Initial kinetic energy, find the final kinetic energy. If they work out to be the same, then it is an elastic collision. And if they don't, then it is an inelastic collision. In this particular case, it is just an inelastic collision. It is not a perfectly inelastic collision, but it is just an inelastic collision. Okay, where the two objects are moving away with two different velocities.
If you like this video, do not forget to share with your friends and subscribe to the channel to watch my future videos. Thank you and see you again.